Question number 51. Correct IUPAC name of the following hydrocarbon is. We have the bond line notation for this hydrocarbon. In this case, if you want to give the name to this compound, we have to start the numbering. We can give the numbers in two ways. One is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. It means it is a decade. Further, this is the first way of the numbering. Further, if I talk about the second way, the numbering should be if we consider this numbering in the first manner, the substituent is present at position that is 3rd, 4th as well as 9th. In this case, substituent will decide what should be the correct way of numbering. Further, if I talk about the second way, in that case, numbering would be in that manner that the substituent is getting the second position first here. You'll see here that second position, then it is at 7th and then 8th position. So, 2nd, 7th and 8th position. In this case, we apply a very common rule, that is first point of difference rule. First point of difference rule. What this rule states, that always you are considering the positions of the substituent. You have to just clearly see that in first way of numbering, substituent is present at the 3rd position, while in second way of numbering, substituent is present at the 2nd position. We always prefer that numbering in which substituent is getting the lowest position in its first point of difference. So here first point of difference is that, and this second way of numbering is providing the lowest position for the substituent. That's why we prefer the second way of numbering. That is here. This is the second way of numbering that we will prefer. On that basis, its name should be 278 because the substituents are present at 2nd, 7th and 8th position and the substituents are methyl group. So 278 trimethyl decane should be the name. And where this name is given? This name is correctly given here in option 3. That's why I'll choose option 3 as the correct option. After this, there's another question. Question number 52. Which of the following IUPAC name is correctly matched? If I talk about the first compound, in this case, there is a ring, cyclopentane basically, and at the cyclopentane, this carboxylic group is present. Its name should be cyclopentane carboxylic acid. Not the cyclopentanoic acid, because in this case, this carbon of carboxylic acid is not the part of this ring and it should be counted separately. That was not done in this case. That's why this name is incorrect. The correct name should be cyclopentane carboxylic acid. Further, the second compound we have, in this compound you can clearly see that carboxylic group is there as a substituent and alcoholic group is also there. Here's the name that's given, 1-hydroxy cyclopent 2N carboxylic acid. Let's provide the numbers to the substituent present here. In this case, the numbering would be in this way. This is the correct numbering, and on that basis, this hydroxy group is present at the 4th position, not at the 1. Further, if I talk about this double bond, yes, it is present at the 2nd position, carboxylic acid. So correct name should be 4-hydroxy cyclopent 2N carboxylic acid. That should be the correct name, not the previous one. So this is also incorrect. This is not correctly matched. Further, there is the compound which is an ester. The name is methyl ethanoate. Just have a look on this group. In this case, this is methyl group that's present with the carboxylic acid group. This is an ester and its name should be methyl ethanoate. This is correctly given. Further, if I talk about the next option, in this case the name is given, that is 2-bromo 1-ethoxycyclopentane. let's provide the numbers to these carbon. In this case, the numbering should be started from bromine in this way. So what would be the correct name in this manner? The correct name should be 1-bromo, 2-ethoxycyclopentane. This should be the name. Means this is also incorrectly given. Which name is correct? The correct name is here given in option 3. So just choose this as the correct option for your question. After that, next question we have. Question number 53. We have two compounds given here and we have to just identify whether they are showing position isomerism, functional group isomerism, metamerism or tautomerism. If you know the definitions of these type of isomerism, you know that what type of isomerism is present here. If you look at these compound, the first one here, it is the amide group. Further, if I talk about this is also amide group. What's the difference? Basically, the functional group given here is 1 degree amide. This is 1 degree amide. While if I talk about the second compound, in this the functional group present is 2 degree amide. Just identify. And these two amide groups are different functional group, not the same functional group. And on this manner, the correct answer should be functional group isomerism. So these two compounds exhibit functional group isomerism and the correct answer for my question becomes option 2. After that, question number 54. Which of the following cannot show tautomerism? If we talk about these compounds in which keto group is here, it means carbonyl carbon is there and we need to just identify those compounds which cannot show tautomerism. We should know that for the tautomerism, always there should be alpha hydrogen present from the keto group. It means we need to just check whether there is the presence of alpha hydrogen or not. If we talk about this compound, in this compound there are 2 alpha carbons, but there is no alpha hydrogen available for this tautomerism, keto-enol tautomerism basically. So we can say there is no alpha hydrogen. If I talk about the second compound, you can clearly see here, this compound can exist as this one. I'm just drawing here. Just have a look on that. Here is the hydrogen atom and the electron of this bond can go this side and these electrons can this way and further. This would be the nature and further can be changed into OH because this hydrogen is coming at this side and further it's forming this field in this way. It means this is the enol form of this given compound and what is going on here, there is 1,5 prototropy that's taking place. Due to that 1,5 prototropy, it is forming its enol form and that's why it is showing tautomerism. Further, if I talk about the third option, in third option there is the keto group and to alpha this there are 2 carbons, but you can clearly see there is no alpha hydrogen atom. That's why no tautomerism. After this, let's check the fourth one also. In this compound, you can clearly see that carbonyl group is present. This is the carbon, but this is alkene. And in this case, this hydrogen is not free for keto-enol, not free for tautomerism. So we can say there is no alpha hydrogen. And that is why there is only one compound which can show tautomerism. It means 1, 3 and 4. These 3 compounds are not showing tautomerism. That's why option 3 becomes the correct option. That says 1, 3 and 4 cannot show tautomerism. After this, it's the turn for next question. Now question number 55. Which has maximum enol content? We have the keto forms which are given here. We have to first check whether they are forming enol form. And further we have to check that particular compound which has maximum enolic content. So in the first compound, if you look at, you will identify that keto group is this. You can clearly see. And alpha to this, there is carbon atom at which hydrogens are present. It means it has alpha hydrogen. What would be its enolic form? I'm just drawing it here. It's enolic form. I'll draw this way, which is here. Hydrogen will move towards this, and ultimately it results in the formation of this type of alcohol. Further, if I talk about the second compound, it will form its enolic form, and in this way you can clearly see alpha hydrogens are present at these sites, and these are involved in the tautomerism, and ultimately there is the formation of the compound in this way. This type of enolic form of this compound would be formed. If I talk about the third option, in the third option, this is the carbonyl group, and along with that there is alpha hydrogen, there's alpha carbon, and this is also alpha carbon, but hydrogen atoms are not available at these positions. It means if there is no alpha hydrogen, there is not the possibility of tautomerism, and there is not the enolic form of this particular keto group. It means in this case there is no alpha hydrogen, and that results in no tautomerism. Now we are left with the fourth option. Here is again there are two keto group. It gets changed into its enolic form. It would be like this, and here is the coming hydrogen from this side. That's why there's a double bond. In this way, if I talk about this, alpha is this carbon, and here would be double bond. This is the enolic form of this compound. This is the enolic form of this compound, and here is for this also. Now we have all the enolic forms. Now your question is, which will have maximum enol content? If you look at the enolic form of the second compound, this is aromatic, and due to its aromatic character, it is more stable in enolic form. While if I talk about this fourth option, this is the compound which is non-aromatic because it is not following 4n plus 2 pi electron rule, and this is non-aromatic. And in the first case, this enol form is there, but this enol form is anti-aromatic. And we know that the most stable one is the aromatic enolic form. It means maximum enolic content would be there with the compound that's given here in option 2. That's the correct answer for this question. Let's take question number 56.